Hi, this is Mrs. Vrobel. This is Chapter 12, States of Matter, Part 5. So today we're going to talk about kinetic theory of solids. So up to this point we've talked about kinetic theory of gases and liquids. And you, from your own experience, know that when you're looking at a solid, such as ice, it appears very differently than it does in the liquid or the gas phase. Reason why? Well, if you notice, solids, they have to have some kind of arrangement with each other. And you probably don't realize this, but they essentially have strong bonds with each other. And as a result of this, they're in fixed positions. The important thing to remember is that the molecules that are in this solid ice actually are moving. They are not just stationary. So they actually have some kind of vibration and they actually rotate while they're connected to other molecules or other elements. Because they are strongly attracted with each other, they do have definite volume and definite shape. So that obviously is a major property of solids. Now I'm going to talk about a couple different things here. We have what we call molar heat of vaporization and we have molar heat of melting. So please note when we're talking about vaporization, we're talking about going from a liquid phase to a gaseous phase, and we're talking about this happening at the boiling point. We also have what we call molar heat of melting or fusion. So we're looking at the heat that's needed to melt a mole of solid at its melting point. So these are going to be important pieces that we need to keep in track of when we're looking at phase changes. So we have a couple different changes, and I'm sure you've seen these before. There's exothermic and endothermic. So please remember that when we're talking about exothermic, we're talking about release of heat. So anything that is exothermic, we're releasing heat. With endothermic, we're talking about absorbed energy. And when we're looking at phase changes, we want to make sure we know which one is exothermic and which one is endothermic. And you might be a little surprised about which one's endo and which one's exo. So looking at endothermic changes, it makes sense, melting. Okay, so me holding this ice cube in my hand, I'm actually adding heat to the solid, and as a result, the solid is becoming a liquid. Evaporation. So anytime you are trying to make the liquid become a gaseous phase, you're adding energy to the system. Sublimation. So sublimation would be dry ice, and I'll make sure I bring some dry ice in to do a demonstration with you. Sublimation, we're going from a solid phase to a gas phase, and in order for that to happen, we need to have energy put into the system. Now, the interesting thing is, and this is something you need to remember, is when we're talking about endothermic phase changes, we're talking about low potential energy becoming high potential energy. So what happens is energy that is found around the solid or the liquid is absorbing that energy, and as a result, we're breaking the attraction between the different elements or molecules, and we're actually increasing potential energy. Now, with all three of these phase changes, we have what we call a cooling effect. So we are not releasing heat into the system, we're actually absorbing heat. Okay, with exothermic changes, freezing. Freezing, you actually release heat by going from a liquid to a solid. Bet you didn't know that. And that's the reason why on refrigerators, they have to have a heat exchanger that removes the heat from the freezer, otherwise everything will melt. Condensation. You may notice that after taking a shower, you're actually warmer while you stay in the shower stall than the moment you get outside the shower stall, because inside the shower stall is condensation. The gaseous molecules are condensing and releasing heat on your body, whereas the moment you step outside the shower stall, it's endothermic, and we have evaporation. And then deposition is going from the gaseous phase to the solid phase. So please note, when we're doing any three of these phase changes, we're going from a high potential energy to a low potential energy. And the reason why is we're essentially forming an attraction with these different elements or molecules. And as we do that, energy is being released into the system. So that's why we get a warming effect as a result with these phase changes. Okay, so you're going to see a lot of these diagrams with these type of problems. Notice that depending on what direction you're going, if you're going upwards, you're heating. If you're going downwards, you're cooling. And notice that wherever you see a horizontal part of the diagram, that's a combination of phases. So notice the green section, we're talking about water and steam. In the purple section, we're talking about ice and water. Wherever you see a diagonal, that's just one phase. All right, what does this mean? Well, when we're looking at the different types of phase changes, notice the heat of fusion, we're looking at very small energies. Heat or vaporization, we're looking at very high energies. And the question is, why do we have such a difference between the two of them? Well, think about it. It's mostly because of the strength of attraction. So when you look at fusion, we're talking about solid versus liquid. Here we're looking at liquid versus gas. The attraction within the liquids is so much higher than it is with gas. And you need to put a lot of energy into the system to become a gas, to break those bonds of attraction. Okay, now we're going to do a series of energy calculations in class. So there's a very important difference between the two types of calculation. You're going to have what we call heating and cooling calculations, and we have phase change calculations. And I will point out the difference between the two. So for heating and cooling, this is the first type of calculation that we will practice, and this is the formula that you need to know. Please note that M is mass, S is specific heat. You have to be given specific heat. And then T is the delta T difference, and it has to be either Kelvin or Celsius. The second type of calculation is a phase change. So notice that with the phase change, you have to look at the number of moles, and you also have to look at the difference in energy. So you have to be given either the heat of vaporization or the heat of fusion in order to do this kind of calculation. So please note, when you're looking at this heating cooling curve, wherever you see a diagonal, this is where you're going to be doing the heating cooling calculations. And with that, you're looking at specific heat, you're looking at change in temperature and the amount of moles. Now, wherever you see the horizontal location with the diagram, please note that that is a phase change. So that one, you're going to need the heat of vaporization or the heat of fusion and the amount of moles to get the amount of heat needed for that phase change. So these are two separate calculations. You may have as much as 5 different calculations that you have to add together, but please note the diagonal calculations are heating cooling calculations and the horizontal are phase changes.